Hi, everyone, once again, and welcome to lecture 9 of the chief strengths in modern cryptography. This lecture will be about three protocols, Saber, Saber, and dilithium. And my name is Andrea Basso, and I'm a PhD researcher at the University of Birmingham in the United Kingdom. And you probably already seen this or know about this, but you know that NIST, the American National Institute for Standards and Technology, started a standardization process that aims at finding the new post-quantum protocols to be deployed worldwide. And currently we are towards the end of round 3, and we are expect within a few days now that the standards will be announced. And in this round 3, there are 7 finalists, the majority of which are based on lattice problems. And in particular, among the lattice-based protocols, 3 are based on the learning with error problem. And these are exactly the 3 protocols that we will be talking about today: Kyber, Saber, and dilithium. The first 2 are 2 encryption schemes, and dilithium is a signature scheme. So just a quick reminder from the previous lecture, the module LWE problem is a problem that asks you to recover a secret vector S, given here, given the matrix A, which is a public known matrix to everybody, and the product between A and the secret vector S plus some error added. So given A and B, the problem asks you to compute the vector S. And in the module variant, this is the components of each vector are polynomials. There is also another variant that you might not have seen before, which is learning with rounding. Learning with rounding is the same as learning with error, but rather than generating the vector E, the error vector, and adding it, the error is then generated deterministically by doing some scaling, which means that we multiply A times S, and then we scale it by fraction P over Q, and then we round to nearest integer. And in this way, the operation is deterministic, so there is no need to have any randomness to generate the vector E. And if the values of P and Q are powers of 2, then what we get is that this operation can be implemented very efficiently. So let's see now how we can use learning with error or any of its variants to create a key exchange. So we have 2 participants, Alice and Bob, and they want to obtain a shared secret of some sorts. So both participants start with generating their own secret and their own error vector. Then they generated a sample of the LWE problem where for Alice is B equal A times S plus E, and similarly for Bob. Then they exchange this vector B and B prime. And now both parties can multiply the vector that they received times their own secret. And in this case, Alice gets this value V, which is one single component, because we're multiplying vectors in such a way that the result is a single element, and the same for Bob. And the nice thing is that now V is almost the same as V prime. And just for reference, throughout this presentation, elements in red will be private to Alice, those in blue are private to Bob, and those in black are usually public. And these have both colors because exactly they are shared by both participants. Now, why are these 2 vectors almost the same? Well, what we get is that Alice computes her secrets transposed times the vector B received by Bob. And if we expand this product, we see that what Alice computes is S transpose times A transpose times S prime plus S transpose E. But now this value, it's the product of a small secret and a small error. So it will be a relatively small value. And then if we look at the computation that Bob does, we see that Bob also obtains exactly the same value here, plus S prime transpose E prime. And what we get is that also this value is small. And these 2 are exactly the same. So if we ignore some small error at the end, we get that most of the two values are mostly the same. Now, what we just seen is a key exchange protocol, but we need to take a step back and discuss different cryptographic primitives to explain how Saber and Kyber actually work. So we have a key exchange, which is a protocol where both parties generate and exchange a public key, and then both parties can use this public information together with their secret information to obtain a shared secret. We also have public key encryption, which is similar, but it's not symmetric anymore. We have Alice that generates a public key and Bob that uses this public key to encrypt a message such that only Alice can decrypt it. And we also have a key encapsulation method, or KEM, which is similar to public key encryption. But again, there is a slight difference. And we have that Alice generates a public key. And now Bob does not encrypt its message directly, but encapsulates a random value, random key. And then Alice decapsulates it, decrypts it. And then this is a shared secret. And the reason why we need this is because in the post-quantum setting, key exchanges are hard to achieve. So this key encapsulation method is similar to public key encryption, but also achieves something similar to a key exchange. So we can sort of see it as the post-quantum equivalent of a key exchange. And we have normal standard ways to transform a key exchange into a public key encryption, and standard ways to transform the public key encryption into a KEM, which is the Fujisaki-Okamoto transform. And so normally when somebody talks about Kyber or Saber, they will always refer to the KEM, the key encapsulation method. But since this can be obtained through some standard transformation, in this lecture, we will only talk about the public key encryption version of Saber and Kyber. So now that we discussed about this, we can see how the Kyber public key encryption protocol actually works. First of all, we have that all polynomials that are used in Kyber belong to this ring that you see here, where it's the ring of polynomials with coefficients modulo Q3329, and the polynomials are also modded by this polynomial that you see here. And key generation is pretty much the same that we've seen before in the key exchange. So we generated a random seed, then we generate the matrix A from this seed, generate vector S, vector E, and then the vector B as an LWE sample. And the only reason why we generate the seed and then compute the matrix A from the seed is because this allows to transmit the value seed A rather than A, which is just a way to compress the matrix. So for simplicity, if you want, you can see this just as the matrix A, but compressed. Then during encryption, the person that wants to encrypt basically generates another value, another LWE sample. So random S prime, random E prime, and B prime using the same matrix A. And then the ciphertext is going to be the vector B prime plus this value C, which is the product of the vector B received generated during key generation times the secret S prime plus the message somehow scaled. And then to decrypt, Alice can simply compute the value V by multiplying this value, this vector B prime in the ciphertext and multiply by the secret S. And what we see is that this value V and this value here is what we saw before in the key exchange protocol. So they will be mostly the same. So then, because they're mostly the same, we can basically use knowledge of C and knowledge of this to extract the message M. And then this is a very high level view of how the protocol works, but different security levels can be achieved by changing basically the size of the matrix and the vectors and the random distributions. But let me spend a little bit more time on what happens specifically here and here and why we're doing this weird scaling. So during decryption, we say we get the message M, and then we multiply by Q, which was 3329, the modulus of each coefficient, and we divide it by 2, and then we round it. And during decryption, we sort of do the opposite process. And the reason is because, so this message M will be 1 bit at a time for each coefficient. So if we visualize the ZQ, the integers mod Q, then we can see them like this because 0 and Q represent the same number. And what we're doing is we're splitting this space into 2, and during decryption, we just look whether during what we received the encrypted value is closer to Q over 2 or is it closer to 0. And if it's close to 0, then we decrypt it as 0. And if it's closer to Q over 2, we decrypt it to 1. And this allows us to get rid of that small difference between V and V prime that I mentioned before. There is just a small catch here, which is that this works most of the time, but in some very rare cases, when the error is very large and the secrets are very large, this leads to a decryption failure. But in general, this is very, very rare and happens with negligible probabilities. Although there have been some recent work that has exploited this to create some attacks that still like only can work with negligible probability because they require decryption failure to happen in the first place. Now that we've seen how Kyber works, we can also see how Saber works. And the two protocols are somewhat similar, but Saber uses the learning with rounding rather than the learning with error, and also uses polynomials that belong to the same ring, but now the coefficient modulus Q will be 2 to the 13th, so a power of 2 rather than a prime number. And then key generation is exactly what we've seen. We generate a matrix A using a seed, we generate a small vector S, and then we generate an LWR sample like this. The public key then is the seed and the vector B. During encryption, the encryptor generates a secret S prime, computes the vector B prime, given a new LWR sample, and then the ciphertext is again this somewhat scaled value, but it consists at its core of this vector corresponding to the public key multiplied by the secret S prime plus the message. And once again, during decryption, the decryptor can compute the value V by multiplying this vector B prime times its own secret. And then the message M again can be occur with some subtraction and scaling, because this V value will be very similar, very close to this value here. Now, before we understand why Kyber and Saber are different, we need to sort of take a step back and look at how these protocols are actually implemented and used in practice. Because the main difference that we see here is that Kyber uses a prime modulus and Saber uses a power of 2 modulus. And intuitively, this should not make a big difference. But it does indeed make a difference when we look at how polynomial multiplication is computed. And polynomial multiplication, as you see, it's a core component, and the whole protocol basically consists of multiplying vectors and matrices of polynomials. And there are several ways to compute multiplication. The simplest way is the so-called schoolbook method, which is just the method that you learn in middle school, where you multiply each coefficient by every other coefficient, and that has O(n) squared complexity, where n is the number of coefficients of the polynomials. And then there is the Karatsuba algorithm that improves on this and achieves n to the log 3 of 2 complexity. And then the same approach can also be generalized to achieve with the Tunkup algorithm, which achieves even better complexity. But the best method, the most efficient way to compute polynomial multiplication is through the number theoretic algorithm, which has complexity n log n, and this can compute polynomial multiplication quite a bit faster than the other methods. And the entity is or number theoretic transform is basically the finite field equivalent of the fast Fourier transform. And it takes one polynomial and it transforms it in the so-called entity form. Now, this does not compute the multiplication directly, but it speeds things up because once we have two polynomials in the entity form, then multiplication is a simply coefficient-wise multiplication. So if you want to compute two polynomials, the product of two polynomials A and B, what we do is that we map them for the entity to obtain the same polynomial in the entity form, which we call A tilde and B tilde. Then we simply compute coefficient-wise multiplication. So we take the first coefficient of one polynomial, the first coefficient of the other, and we multiply. The second coefficient of one polynomial, the second coefficient of the other polynomial, and we multiply, and so on. And then the magic part, the nice part, is that if we apply the inverse entity, which is exactly the operation that maps a polynomial from the entity form to its original form, what we get is exactly the product between A and B. And this is very efficient because this entity operation has complexity O(n) log n, and then this operation has complexity O(n) because it's just linear in the number of coefficients. So this is asymptotically the fastest way to compute polynomial multiplication. But there is a catch, and it requires that the ZQ has a specific root of unity, which in turn requires that Q is prime. So this means that Saber can compute polynomial multiplication with this, but not Saber. So now we can see the comparison between the two, and we see that Saber can use the entity algorithm, and it just doesn't enable to use it, but it requires implementation of Saber to use it, because when we have that step where we take the C, then we map it to the matrix A, that step already generates the polynomials in the entity domain. Whereas Saber does not allow this, so other type of polynomial multiplication are required, but this is more flexible, so the better approach for the specific use case can be used. There are also other differences because this is different implications. And for instance, we see that Saber has the best performance, especially in software implementations, whereas Saber cannot use the NTT, so it's a bit slower in software, but then it makes up for this with faster implementations in hardware because the flexible approach allows it to get a small margin. And then we also have that the LWE problem is better studied, so we think we understand the security of Saber a bit better, whereas Saber uses the learning with rounding, which allows to have slightly smaller ciphertext. And Saber also has been implemented on a wide variety of platforms and by a wide variety of people. So there are a lot of studies in that regard, whereas Saber has fewer implementations, but we see that, for instance, Saber has better side channel protection. And I won't get into what side channel protection means, but at a high level, it just means that if you want very, very, very protected implementations from very explicit type of attacks, then Saber performs a bit better. But in general, we see that Saber and Saber are both modern protocols that are fast, secure, and efficient. Now that we covered encryption, we can move on to digital signatures. And here we also have two different types of primitives that it's important to distinguish. So we have an identification protocol where Alice basically wants to prove knowledge of a secret. And the way that it does is that she generates a public key and a commitment. Then Bob sends a challenge value and Alice responds to this challenge. And then Bob or anybody else can verify that this response is the correct one to the right challenge. And Bob then knows that Alice knew the secret that Alice wanted to prove knowledge of. We also have digital signatures, which are somewhat similar, but they somewhat mimic what in real life, when we sign a document, So we have that Alice wants to sign a message, as in proving that she generated or she did the message, which means that like only Alice can create a valid signature. And the way that this happens is also similar, but there is no challenge part. So Alice creates a public key, signs the message, and then Bob or anybody else can verify authenticity of the signature. But there is, again, a classic transformation from one to the other, which is called the Fiat-Shamir transformation. So for dilithium, we can start by looking at the identification protocol, and then we'll see how that is transformed into a signature. Key generation, again, is very simple. We start with a mod LWE problem, and we generate the sample. So we generate S, E, and the public key then will be the matrix A, or again, a C that generates the matrix A and the vector B. To commit, we generate a random vector Y, compute the product between A and Y, and then commit to the highest bits of this. So we just drop the lowest bit of these values. And then Bob sends a challenge C, and Alice can respond to this with the vector X, Z, equal to Y plus S, the secret times C. And to check that the response is correct, then Bob can simply check the view W, the value that was committed, is exactly the high bits of this value here. And the reason why this is correct is because if we look at these values up here and we expand it, we do all the computations, and then we get that this is exactly A times Y minus E times C. But now we know that E is a small error and C is a small challenge. So A times Y minus EC will be roughly the same as Y. So if you only look at the high bits and we drop the lower bits, then this will be the same. Now that we have the identification protocol, we can then transform this into a signature protocol. Key generation is again the same. We generate a model WE sample. Then to sign, we generate a random vector Y. We generate the vector W, again, as in the commitment before. So we multiply A times Y and then look at the high bits. And then there is the so-called the Fiat-Shamir step. So what we do is that we take this commitment W, we also look at the message that we want to sign, and we apply a hash function to the concatenation of the message and the vector W. And what we get is that the challenge C is then deterministically generated from the message and W. And then the signature consists of the challenge C, basically, that we generated deterministically, and the answer to the challenge C, so the value Y plus SC. And then verification is pretty much the same as before. So before we wanted to check that these high bits were the same as the value W, but now we don't have this W anymore. So what we do instead, we generate W prime, and then we check that this W prime together with the message lead to the challenge C that was actually published here. So in this way, Alice can sign any message M, and only Alice can sign this, because if you don't know the value S, nobody else can forge a signature. And then, I mean, this is a high level view of the protocol, but the specific protocol uses a prime modulus where it's given here. So it allows the usage of the entity the same way in Saber, and it's actually required. There is, however, a catch, in the sense that the protocol that I just described is actually insecure, because the signature can leak information on certain specific cases, not all the time, only just some cases. So what happens is that we can fix this by checking if the coefficients of C, the signature that we generate, are in a certain range. As long as they are in this range, then the signature does not leak anything. If they are outside of this range, then they leak. So what we do is that we check if they are in the range, And if they're not, we just start again with a new random vector y. And if that's, and we keep repeating this until we get something that is in the right range. And we see that in practice, this requires to repeat this signature process about 5 times. And lastly, the full protocol also applies some compression techniques that only provide the high bits of Z rather than the entire coefficients of Z. And in this way, we can get smaller signatures without impacting the execution time too much. Okay, so just to sum up what we see, I know it was a very fast overview of 3 different protocols, but if there is like a takeaway, is that like they're all 3 solid protocols that are fast and secure, and we know that probably one or more of these protocols will be chosen for standardization, and we'll be hearing about this very soon. But I also don't want to give you the impression that this is all work that has been done, completed in a few weeks, and NIST announced the new standard, and everybody moves on to do new things. This is still a very bubbling and active research field. And there are like several research directions that are being explored, but still require lots and lots of work. And these span from the most theoretical to the most practical implications. And for instance, I just listed a few examples here. We definitely need to further study the security of the LWE problem, the mod variant, the LWR variant, whether we can reduce one to the other, and so on. Then at the protocol level, we also want to research whether it's possible to get new protocols, maybe similar to what we have, but maybe somehow make them faster or smaller or more efficient in specific use cases. Then more on the applied side, we also have research questions involving how, okay, now that we have the protocol, how do we actually implement this in software and hardware on a wide variety of platforms, and how do we make this actually run efficiently and as fast as possible? And lastly, we know that this or other protocols will be standardized and will have to be deployed, but the peculiarities and characteristics of these protocols are very different from those that the classical protocols that we are using right now. So there will be also a lot of work required in figuring out how we can actually replace the currently used protocols with the new post-quantum ones. So there will be definitely lots and lots of work to do. So if you're interested, there is definitely lots of questions that you can work on. Thank you very much for your attention, and I'll be happy to take any questions.